Now let's talk about section 12.2, systems of linear equations from the viewpoint of matrices. So 12.2, systems of linear equations. Matrices. So for example, if we have this system of linear equations, the simplest one, we just pick up x plus 4y is 14 and 3x minus 2y is equal to 0. Well, we can use x and y to represent the unknown variable. We can use other letters. For example, we can use s plus 4t is equal to 14 and 3s minus 2t is equal to 0. So you will solve these two different, well, they look different. So you will solve these two different linear equations, but you will get exactly the same solution because you only change the name. You still have the same system. So this system looks not depend on the x and y. They depend on those numbers. Those are so-called coefficients. So x, y, they actually just represent the position like a first variable, second variable. So x has coefficient. See here, there's no coefficient. The coefficient is 1. We copy the coefficient of x, 1 here. Correspondingly, y has coefficient of 4, so we're going to copy 4 here. In the second equation, you have coefficient of x, 3. Y coefficient is -2. Be careful, when we get coefficient, the coefficient contains the sign. If it's minus 2y, the coefficient is -2. And this constant number, because those constant numbers are from the other side, so we draw this vertical segment to represent or to remind us the equal sign. So here's a 14, the position here is a 0. So thus 1 is the coefficient of the first variable, 4 is the coefficient of second variable, 3 is the coefficient of first variable, -2 is the coefficient of second variable. On the right side of this vertical segment, they are the constants from the right-hand side. And we put them like this. You can use parentheses or you can use brackets. They both work, okay? So you use either parentheses or like the textbook, they use bracket. The same thing. 1, 4, 3, -2. We draw the vertical segment and put 14 and 0. This vertical segment, again, just remind us the equal sign. Okay, so this type of stuff is called a matrix. It is called a matrix. So let's see the definition. A matrix is defined as a rectangular array of numbers. So they are all numbers. And once you have array, once you have array, they are placed in certain order. So we'll have A11, A12, A13, A1n. It looks like this row comes from the first equation. 1 means the first equation, first row. And then you have A21, A22, A23, A2n. Okay, the second row. And in general, you will have a I1, the ith row, first element, the number corresponding to the first coefficient. AI2, AI3, AIN. And between them, if you want to say, okay, what is a J's position? This is the first position, second position, third position. If you have a J's position here, it becomes A1J. Here is a A2J. The second row, J's position. Here is a I's row, J's position, AIJ. This number we write AIJ. I's row, J's position. And finally, assume you have M equations, so you will have M rows, AM1, AM2, AM3, the J's position, AMJ, and finally, you have AMN. And you use brackets or parentheses to include them. This is called a matrix. So this is a I's row. This is J's column. I's row, J's column. The first one, I, is a row index. This J is a column index. Every number has two indices. It has a row index and a column index. So each number from the matrix Aij is called an entry. An entry, okay? How many numbers are there in this matrix? You see, every row has n numbers. They have m rows. So in total, there are m times n numbers. So there are m times n numbers. Okay? So this is a matrix. You just put a rectangular array here in order, and you will have a row, you have a column. Row and a column. Okay? So this is a generalization of those matrices. Okay. And this matrix, the matrix used to represent a system of linear equations is called the augmented matrix. Augmented matrix. In the augmented matrix, there's an additional vertical segment. This additional vertical segment just tells us on the right side, they are the constant numbers from this system of linear equations. All right? So the system of linear equations essentially depend on those coefficients. They don't depend on the name of variables. You can name them in whatever way. You can even name this as x1, this is x2, or name them as s and t or x and y, whatever favorite letter you want. Okay, and you get certain pattern, certain array, and this array is generalized to m by n matrix. This matrix has a dimension. What is a dimension? It has m row, n columns, so it is m by n matrix. It is m by n. M means m rows, n means n columns. Each number from this matrix is called an entry. There are m times n entries. Here, this AMN does not mean m times n. It means m is m's row, n means nth column. Okay, they are indices to locate this A. Okay, so for example, let's see the more example. if we have a system linear equations like 3x minus 4y is equal to negative 6, and 2x minus 3y is equal to negative 5, then the corresponding augmented matrix is 3, 2, negative 4, negative 3. Remember this vertical segment. This vertical segment is not a standard notation in the matrix. It is a standard notation in the augmented matrix. And then you put a negative 6 and negative 5. It only reminds us this is augmented matrix, and this is a position of equality. That's left-hand side and right-hand side. Right? This is two equations of two variables. If you have, for example, three equations of three variables, 2x minus y plus z is equal to 0, x plus z minus 1 is equal to 0, x plus 2y minus 8 is equal to 0. All right? So in order to write the augmented matrix, you have to have the standard writing. So here, you see, we are going to write in the following way. X always in the first position. Y always appears in the second position. Z always appear in the third column. And all the constant numbers will be placed in the right-hand side of the equation. So for example, first one is okay. So you don't move anything in the first equation. It is placed very well. And second one, see here, x is okay. There's no y, you skip it. Plus z, so you just put plus z. And this 1 should be moved to the right side, plus 1. And the third equation is x plus 2y, no z, so you don't write it. Minus 8, you move 8 to the right side. Okay, you move 8 to the right side. And based on this equivalent form of the system equations, we have the augmented matrix 2, 1, 1. So the column 2, 1, 1. They are the coefficients of the same variable. Negative 1, here no y means coefficient is 0. Negative 1, 0, and 2. 1, 1, 0. 1, 1, 0. And vertical segment 0, 1, 8. Okay, so this is the corresponding augmented matrix. The corresponding augmented matrix. Okay. If you don't want to always copy the constant numbers from right-hand side, if you just focused on the coefficients of variables, so for example, this one, for the first one, we can write 3, negative 4, 2, negative 3. We just write the coefficient, copy the coefficients of x and y variables. Then this is called, all the numbers are coefficients, so they are called the coefficient matrix. Okay, this is coefficient matrix. And this one, so 2, negative 1, 1. I just copied this part. The part on the left-hand side of this vertical segment. 1, 0, 1, 1, 2, 0. This is also, is the coefficient matrix. For part B, this is coefficient matrix for part A. Okay, so coefficient matrix is a part of augmented matrix. Augmented matrix contains all information. Coefficient matrix only contains the information of variables. All right? So for example, if the augmented matrix is what? Let's see, is a 5, 2, -3, 1 vertical segment, 13, -10. Then what is the corresponding system of linear equations? The corresponding system of linear equations is, well, usually we use x and y. We usually use x and y for 2 variables, x, y, z for 3 variables. Okay, so here you see 1 position, 2 positions, first position, second position. There are 2 variables. So we will use 5x plus 2y is equal to 13, and -3x plus y is equal to -10. So this is a reconstruction of a system linear equations from the given augmented matrix. And it's A. B, if the augmented matrix is given by this one, so 3, -1, -1 vertical segment, and 7, 8, 0. I just tried 2, 0, 2, 0, 1, and 1. Okay, so assume this is augmented matrix. How do I know it's augmented? You see the vertical segment and the right, left side. Then the system equations is, okay, so x, y, and z. So 3x minus y and minus z. Plus -1 times y. Plus -y is minus y. Here is minus z. Is equal to 7. 2x, 0 times y disappears. 2 times z plus z is equal to 8. 0 times x disappears. 1 times y. 1 times z is equal to 0. Okay, so this is a corresponding system of linear equations with respect to the given augmented matrix. Okay? Okay, so let's try to manipulate this matrix and see what we can do. Remember that let's just get the simplest case. Let's put x plus y. X plus y is 1. X minus y is 0. Let's just select a simple example. So the corresponding matrix is this one: 1, 1, 1, -1 vertical segment, 1, 0. This is augmented matrix. For these 2 equations, we can call this as, we can place this as the first equation, this second one, or we can switch them. So we can switch them. If we switch them, we'll get this one. This one, what is the corresponding augmented matrix? It is 1, -1, 0, 1, 1, and 1. So based on this augmented matrix, what we do, we just exchange 2 rows. Well, based on the common sense, we only exchange the position. We do not change the solutions. So solutions are kept or remain same. Solutions remain same. Remain, or whatever. I remain same. Okay. So what we can do for the rows, we can exchange rows. We can place a row 1 as a row 2, row 2 as a row 1. We don't change the solutions. Remember, of course, I can just randomly modify an entry, a single entry. But if I do that, I cannot guarantee if I still have the same solution. Remember, our goal is to solve the system linear equations. We can do something, but we cannot change the solution. So exchange two rows, solutions are kept, remain the same. And second one, we'll talk about this equation. I can multiply the first one by 2. For example, I have a 2x plus 2y is equal to 2. And second one, I keep it. X minus y is equal to 0. You know that when we multiply the row by a non-zero number, so this equation is equivalent to the original one. Okay, so here I copy the corresponding augmented matrix. Okay, so from here to here, what do? We just multiply a row by what? By a constant non-zero number. We multiply a row by a constant non-zero number. It have to be non-zero. If you multiply by 0, they're both 0, so it's not interesting. By a non-zero number. You still have the same solution. You still have the same solution. Okay? Solutions remain the same. Yeah, now I know how to write the remain. Okay, so this is usually the certain operation we can do in order to solve the linear equations. Or we can do what? We can add two rows. We can add two rows. So for example, we add this row to this row, we will get x plus y is equal to 1, and you do this addition, add these two rows, you will get a 2x is equal to 1. X plus x, 2x, y plus negative y, cancelled, 1 plus 0 is 1. So the corresponding coefficient, augmented matrix is 1, 1, 1, and 2, 0, 1. How do we get the 2, 0, 1? You just really add the first row to the second row. So you see 2 plus 2 is 2, 1 plus 1 is 2, 1 plus negative 1 is 0. 1 plus 0 is 1. 1 plus 0 is 1. So we can add a row to another row. But we still have the same solution. We have the same solutions. Okay, so you can recall in the elimination in the elimination process, we actually just do those steps to solve the system of linear equations. So these three operations are essential in the matrix study. So they are called the row operation. So let me. What is a row operation? Number 1. Interchange any two rows. When we say them, we mean we keep the solutions unchanged. Interchange any two rows or replace a row by a non-zero multiple of that row. Replace a row by a non-zero multiple of that row. Just means you just multiply this row by a non-zero number. and 3. Replace a row by the sum of that row and a constant non-zero multiple of some other row. So here we have one more operation. We sometimes, here this one is simple, so we just directly do addition. If, for example, here is a add 2, assume there's a number 2 here, we have to multiply the first row by 2 and then we do addition. Remember that? We multiplied by 2 and then we added to the other equation and cancel the y, the elimination method. So you can do the multiplication first, constant non-zero multiple of some other row, and then add to the other row, to that row. So that is the same as this one, the third step. Okay, so we have 3 row operations, and they are enough, and they will preserve the solutions. They are enough, and they will preserve the solutions. Okay, so let's see. For example, we will see the example. We have an augmented matrix 1, 2, 3, 4, -1, and 2. We have this augmented matrix. So we want to do certain row operation. All right. So what is it? We are going to multiply the first row by -4 and add it. You see, first row, usually the original row, we use a little letter, row 1. We're going to multiply it by -4. So this 1 becomes -4. And we add it to the second row. So -4 plus 4 is 0. So canceled. So we multiply row 1 by -4 and add it to row 2. And the result becomes a new row 2. They are not equal sign, it's an implication. So 1 times -4, -1, plus 4 is 0. 2 times -1, you have to multiply this row by every number by this -4. -4 times 2 is -8, plus -1 is -9. 3 times -4 is, you see, it becomes -4, -8, -12. -12 plus 2, -10. And first row unchanged. You see here? You multiply -4, multiply the first row by -4. You get a -4, -8, and -12. And you add them to 4, -1, 2. You get 0, -9, -10. Okay? 0, -9, -10. This is the third operation. Multiply a row by a non-zero number and add it to another row. And this process will give us some 0. We want some 0 happen. This is actually the elimination process. All right? So for example, let's see. If we want to apply this operation, we have to understand what is the operation, the meaning of the operation, to this matrix, augmented matrix, 1, -2, 2, 9, right side, left side, 3, -5. Okay, so what does it mean? R2 means the new second row. So here, this one just means first row is unchanged. Let's just copy the first row. And the operation means we're going to multiply the first row by -3. Let's check. First row becomes -3. 1 times -3, -3. -2 times -3, 6. 2 times -3, -6. And then we add them to row 2. 3 plus negative 3, 0. Negative 5 plus 6, 1. 9 plus, this is addition. Check here, this is addition. 9 plus negative 3 and negative 6, 3. So after this operation, you keep the first row unchanged and second row becomes 0, 1, 3. 0, 1, 3. Okay, so this is the meaning. What it means for this capital R2 is equal to negative 3 little r1 plus r2. Usually in this section, little r1, r2 means the original row. Capital R means the result row. Okay, another example. We have an augmented matrix. Okay, the requirement is that change the entry in row 1, column 2 to be 0. We want to change the entry in row 1 and column 2 to be 0. How do we do that? So first you have to know which entry we are talking about. Row 1, this is row 1. Column 2, this is column 2. So we are talking about this number. We want to make this number 0. Of course, we try to do it by row operation. Remember, we only do it by row operation, So how do we do that? We can, we can multiply the second row by 2 and add the twice of second row to the first row. So our new first row becomes the first row plus 2 twice of the second row. All right? So in this process, the second row is unchanged. We only change the first row. Okay, 2 times 0 is 0, plus 1 is 1. 2 times 1 is 2, plus negative 2 is 0. 2 times 3 is 6, plus 2 is 8. So this is a new first row after the row operation. New first row after the row operation. All right, so here we do have the basic concept. We have the matrix, we have the row operations. And next, we are going to use the row operation to find the solutions of the system of linear equations. We are going to discuss the detailed example and the process in the next video. Thank you.